We are building a bridge between group theory and linear algebra by representing each group element as a matrix. We've discovered that we can often make all of these matrices diagonal, so that the representation breaks apart into much simpler, one-dimensional representations. The problem is that finding these one-dimensional representations isn't exactly easy. Sometimes you can use your geometric intuition, sometimes you need algebra and the complex roots of unity, sometimes you have to reason about permutations. There doesn't seem to be a single strategy that you can follow in all possible cases. Character theory is a set of miracles that helps us find all of the irreducible representations of a group. I use the word miracles here because this theory is totally unexpected and really cool. It's also very advanced, so I won't be able to prove everything in detail. I will do my best to give you some good examples that clarify all the miracles. The first question we should answer is, what are characters? The basic idea is actually really simple. Start from a group such as C4, the familiar rotations of the square. Map each group element to a real or complex number. The mapping must be a homomorphism, so that the binary group operation gets mapped to complex multiplication. That's it. Such a mapping is called a character. Let's do a specific example. We will map the group elements, the rotations of the square, to the numbers 1 and -1 in a consistent way, so that the mapping is a morphism. As always when constructing a morphism, the neutral element of the group, the 0-degree rotation, must be mapped to the neutral element for multiplication, the complex number 1. We can then decide where to map the generator, the 90-degree rotation. Once we make that decision, all the other group elements follow from the generator. This mapping is our first example of a character. Let's see if we can find more examples. This one is pretty boring. It's known as the trivial character, and it just maps everything to the number 1. With a bit of effort, you can also find these two characters, which make use of the imaginary unit I. You can check that these are morphisms. 90 degrees plus 180 degrees is 270 degrees. And if you map everything over to the complex numbers, you get I times -1 is -I. These four are the only possible characters for our group. That's actually quite easy to prove. Think about the generator, the 90-degree rotation. After 4 of those rotations, we end up back at the identity. So the generator satisfies a simple equation. Its 4th power equals the 0-degree rotation. When we map it to a complex number, the morphism makes sure that the equation still holds. After all, a morphism maps every relation between group elements to the same relation between the numbers. So we know that this complex number must be a 4th root of unity. There are only 4 of those available, and as soon as we pick one of them, the rest of the group follows automatically. This explains where the 4 characters come from. Now, at this point, many of you are rolling your eyes, because I'm just repeating everything from the previous video. We used exactly the same line of reasoning to show that there are only 4 possible one-dimensional representations. We wrote them all down, and the numbers in those matrices were identical to the numbers we have here. Every time you have a character for a group, you can just put square brackets around the numbers and you have a representation with 1-by-1 matrices. And you can also do the opposite. Starting from any one-dimensional representation, you can remove the brackets and you have yourself a character. There's no fundamental difference. In the literature, you may even encounter the term character as a synonym for a one-dimensional representation. And so you might ask, why do we even need characters if they don't teach us anything new? That's a fair question. The full power of characters will become apparent only in the next video, where we will see that you can calculate characters for larger matrices, such as 2x2s and 3x3s. The link between those matrices and their characters won't be as trivial anymore as just removing the brackets. For now, by removing the brackets, we just get a nice table that gives us a much better overview of all the available characters. This is known as the character table. I want to stress that a character table contains only the irreducible characters for a group. A group has many other characters, infinitely many of them in fact, but just like the representations from the previous video, they can all be constructed from a small set of fundamental or irreducible ones. I'm going to put a few character tables for different groups on the screen. These are the tables for the cyclic groups with 2, 3, and 4 elements. The one with 3 elements gives us the rotations of a triangle, or addition modulo 3. You already know the one with 4 elements as the rotations of the square, or addition modulo 4. I also show the Klein 4 group, which you can think of as the symmetries of a rectangle, including reflections. The reason I pick these 4 examples is because these are all Abelian groups. They are commutative. We learned in the previous video that Abelian groups can always be broken down into one-dimensional representations. And then all we have to do is remove their matrix brackets to obtain these character tables. First, I should tell you how to read these tables. At the top of each column is an element from the group. For the cyclic groups, I use the integers modulo n. For the rotations of the square, I show the names of the rotations. And for the Klein 4 group, you get the symmetries of the rectangle, 2 rotations and 2 reflections. Each row of the table is a character, which maps all the group elements to their associated complex numbers. So this particular character maps the neutral element, the 0-degree rotation, to the complex number 1. It maps the 120-degree rotation to eta, which is a third root of unity. And it maps the 240-degree rotation to the other third root of unity, which is eta squared. As you can see on the diagram, the third roots of unity correspond exactly to the corner points of an equilateral triangle, which gives you a strong intuition for why these specific complex numbers play a role here. Complex numbers are good at rotating. The third roots of unity specifically rotate over multiples of 120 degrees. Each relation between the rotations of the triangle gets mapped to the same relation between these roots under complex multiplication. So we do indeed have a morphism and therefore a character. In the first row of each table, I have placed the trivial character. It maps everything to the number 1, which is a very easy but boring way of satisfying all the requirements for a morphism. These trivial characters correspond to the trivial representations we saw last time, minus the brackets. You probably noticed that all of these tables are square. Using character theory, it is possible to show that an Abelian group with n elements always has exactly n different characters. We are now ready to look at the first big miracle. Take 2 different characters, such as these 2. Treat them as 2 vectors. So think of the entries in the row as the coordinates of a vector, in this case a 4-dimensional one. This may seem like an odd thing to do, but look what happens when we calculate the dot product of these 2 vectors. As always, we just multiply the coordinates pairwise, and then we add everything up at the end. The result turns out to be 0. Okay, what happens if we take these 2 characters? You can calculate their dot product yourself. You should again get 0 as a result. Try a few more examples to convince yourself that it always works. Well, maybe this is just a coincidence. Maybe K4 is just special. Let's try the same thing with two characters of the C4 group. This time, when you perform the pairwise products and add everything up, you don't actually get 0. Ah, bummer. It seemed like we had something going there, but it doesn't work for this particular group. But wait, remember that we are dealing with complex numbers here. So it makes sense to replace the traditional dot product with this slightly different version where you take the complex conjugate of the second number each time. When we use this more advanced kind of inner product, we do end up with 0 again. Okay, we're back in business. You can try a few more examples and you will see that it works every single time. Our new inner product, applied to different irreducible characters of the same group, always yields 0. I am not going to prove this miraculous result, but we can give it a kind of geometric interpretation. We could say that the irreducible characters of a group are orthogonal to each other, at least with respect to this specific inner product. Remember that two vectors are orthogonal when their inner product is 0. But what does orthogonality mean in this particular context? Earlier, we dedicated an entire video to Fourier analysis. I explained that functions, such as sine and cosine waves, can be treated as vectors, and that orthogonal functions can be used as a basis to construct other functions. That's how generic sound waves are created from simple basis waves. Here we have a different kind of function. A character is a function that maps the elements of a group to a set of complex numbers. The fact that these functions are all orthogonal to each other implies that we could use them as a basis for other group-related functions. This leads to a new kind of Fourier analysis on finite groups. We cover this in a separate video, which is available exclusively on Patreon. So, if you're curious about the connections between character theory and finite Fourier analysis, follow the link in the description below to set up your Patreon account. Thank you for your support. Whenever you discover a new inner product, it's always a good idea to see what happens when you multiply a vector with itself. This gives you the squared norm or length of the vector. If we do this for the characters, we seem to always get the size of the group as a result. So this is the second miracle. Under the inner product we have defined, the squared norm of each character function turns out to be exactly equal to the size of the group. If you want to try this out yourself, remember that the conjugate of a root of unity simply has the opposite angle. When you multiply the root with its conjugate, you add up the angles, and they always cancel each other, so the resulting angle is 0. That's why the product of a root of unity with its own complex conjugate is always 1. This happens for every value of the character. And then we add up all those ones exactly n times. So it makes total sense that we get the group size at the end. This result is just shouting at us to redefine our inner product one last time. We should divide the end result by the size of the group, which is written like this with the group name between vertical bars. This is how you normalize the inner product. The zeros we got before will still be 0, but the norms of the rows now all become equal to 1. And that means that our character functions are not merely orthogonal, but orthonormal. That makes them a perfect basis for other functions on group elements. You can verify that the columns of these tables are also orthonormal under the same inner product. But wait, that seems to imply that these tables are orthogonal matrices. They're all square, and they all have orthonormal rows and columns. That's exactly the definition of an orthogonal matrix. But that is just crazy. It's totally insane. Remember that each number in this table is itself a little 1-by-1 matrix. We just placed all of them together in a handy table, but now it turns out that this table itself is a matrix at this higher level of abstraction. In the next video, we will have another look at this incredible meta-matrix, because it's going to get even crazier. If you're like me and you love intriguing connections between different domains of math, here's a fun one that's easy to understand. Number theory is an area that doesn't seem to be connected to matrix representations and characters at all. In number theory, we deal with ideas such as prime numbers and prime factorization. Now consider the divisors of a given number n. For n equal to 12, we have 1, 2, 3, 4, 6, and 12 itself, which gives a total of 6 divisors. A prime number like 13 only has 2 divisors, 1 and the number itself. We now define a function called sigma, which maps each number to the correct count. So sigma of 12 is 6, and sigma of any prime number is 2. You can quite easily prove that this function is multiplicative. What this means is that if you take two different numbers that have no factors in common, like 2 and 3, their product, 6, has the product of the function values. Another example would be 3 and 8. They have 2 and 4 divisors respectively, and their product, 24, has 2 times 4 divisors. When you write out this property formally, you get an equation that looks like this. The value of sigma for the product of m and n must be its value for m times its value for n. I hope you recognize this kind of formula. It's the definition of a homomorphism. And since our character functions are all required to be homomorphisms, we can now think of them as multiplicative functions, just like the divisor function sigma. This is the link that gives characters a central role to play in number theory. Certain kinds of characters can be used as the coefficients of a Dirichlet series. It's similar to a power series, but with the input variable in the exponent instead of in the base. These functions are crucial for analytic number theory. If you use the trivial character, all the coefficients become 1, and the resulting series is known as the Riemann Zeta function. Its properties, and in particular the position of its zeros, its roots, are the subject of a $1 million prize. Other characters result in functions that are similar to zeta, and mathematicians are frantically studying them in order to find out how they work and what they can teach us about the prime numbers and how they are sprinkled between the other integers. So you see that there is a lot riding on these character functions. Because of their central role in number theory, characters are also used a lot for counting things. One of my all-time favorite math videos is this one by 3Blue1Brown, where he counts the number of dots inside a circle to get an approximation for pi. Near the end of the video, he introduces a function called chi. The Greek letter chi is often used for characters. The fact that this chi is multiplicative plays a central role in the counting process. Go watch the video, it's incredibly pretty and satisfying. The word character is meant to suggest that these complex numbers characterize the group in some way. And that's absolutely true. Two representations are essentially the same if they have the same character. So instead of looking at matrices, we could simply look at complex numbers instead, which is much easier. This is going to become even more important in the next video, where we will look at matrices that aren't 1 by 1, but bigger. You can already watch that video right now on Patreon. And don't forget that there's also a Patreon exclusive video with more details about finite Fourier analysis. Please like and subscribe, and I will see you next time.